Hi, my name is Tarun Awala, and this is Lab 4 Magnetic Field of a Bar Magnet. So, the goal of this lab is to investigate how the magnetic field of a small bar magnet essentially changes with the distance, and we compare our experimental measurements to theoretical predictions based on the Beer-Savart law, which focuses on the magnetic field along the axis of the magnet and the magnetic field off the axis. And the results derived throughout the experimentation for the power law exponent was n equals negative 3.234, and then the magnetic dipole moment, which was 3.954 am squared. Some of the fundamental principles that were utilized in the lab were the BSOR law, essentially describes how the magnetic field at a specific point is related to a very small segment of current, and then the distance dependence formula, which is the strength of the magnetic field from a bar magnet, it decreases as you move farther away from it, and then the magnetic field of a dipole. And this explains how a magnetic dipole can be thought of as a loop or a closed path of electric current. Now let's get on to the experimental procedure. We positioned the phone so that the magnetometer is perpendicular to Earth's magnetic field in the beginning. And then after that, we located the position of the magnetometer sensor within the phone. And then lastly, we measured the distance between the magnetometer and the bar magnet for the both on axis and off axis configurations. And this is our graph and data for the on axis situation. And on the left, we have the predicted graph and also the slope, where we got y equals negative 3.435x minus 12.859. And these also replace the constants in the equation above, which enabled us to derive the n that we need for the distance dependence formula. And this is the off-axis data, and we can see how the distance is perpendicular to uh, reference point on the magnetometer on the phone. Now onto the computational model. So first we just set our physical constants. There weren't that many, and then we created the actual magnet at the origin, and then created the dipole moment B, and then we got the results on the right where the arrows depict the magnetic fields, and also the magnitude of B at 45 degrees is 2.93584 to times 10 to the negative 5. So pretty small. Some of the assumptions and errors that we spelled errors wrong, but some of the errors that we encountered were that the bar magnet behaves like an ideal magnetic dipole. This was one of the assumptions. And the second assumption was that the magnetic field decreases as the distance from the magnet increases. So some of the errors that we had were that the nearby electronic or magnetic objects may have interfered with the distorted the magnetometer readings, and also the exact position of the phone's magnetometer sensor was not determined with high precision. So some of the observations that were seen throughout the lab, the first two um, are true observations, and the ones highlighted in red are observations which were not true in the lab. And then finally, on to the discussion questions. So, what if we didn't adjust for magnetic north and instead place the meter stick at some angle relative to Earth's magnetic field? And in that particular case, Earth's magnetic field would mix with the bar magnet's field, which would cause an interference and leading to an inaccurate or skewed measurement. And second question was, what if we connected two identical magnets end to end and repeated the experiment? For this, the strength of the magnetic field would increase roughly double, I guess, and then but the overall direction of the field would remain the same. Thank you for listening.